series crunching. Okay, all right. So this is the first plot. I hope you find this plot super exciting. Only nerds find plots exciting, but you're all nerds. Right. So this is a very exciting plot. When I saw this, I'm embarrassed to say the first time I saw this plot was when Mark gave his practice talk. Before the FSE gave a practice talk. I didn't even know this was going on in Davis, the lab next door. We never talked, right? And then I found this and I thought, this is really interesting. What does it mean? All right, okay, so here's the plot. I'll first, I always like to do this. I first like to sort of make sure people understand the coordinates, and then we can sort of look at the plots in more detail. So this plot has 8 different plots. On the x-axis is the granularity we're trying to match. Okay, so we're trying to match sequences of 5 tokens, roughly a line. Okay, and we're trying to match sequences of 65 tokens, maybe about half a method or a method, something like that. And what we're going to do is we're going to see how many of these are repeated. So the y-axis is a percentage, right? If it's 100%, it means everything is repeated, right? There's nothing unique. So if you have the same 65 sequence of code over and over again in all of open source in GitHub, then it'd be 100%. Everything from 3 to 5 to 65 would get 100%. It's all repeated, right? Nothing is unique. Of course, we don't have that. Right? So the y-axis percentage of repetition and the x-axis is this. Okay, now we have several different plots. The top one is, so let's start at the bottom. That is, we're not going to consider variable renaming, the bottom plot, and we're not going to allow any changes. Right? It's be exactly the same. Right? Then above that, we have no abstraction, that is all variable names are exactly the same, but we allow one token to be different. Okay? And then the next set is exactly the same as that, except now we allow variable renaming. Okay? So we have no edits, 1 edit, 2 edits, 3 edits, and then we have no abstraction and abstraction, so we have 8 different ones. Okay? Any question about this? What would you expect the shape of this plot to look like? Increasing, decreasing? Quickly increasing, decreasing, very good, okay. And how would it decrease? Would it be decreasing uniformly, decreasing non-uniformly? I'm trying to build excitement here. Okay, okay, so that's what it looks like when you allow renaming and up to 3 changes. So all these plots to me are really remarkable, right? So this basically shows you that how repetitive code is, right? It's like, up to about 25, 26 tokens. If you allow a few edits, almost none of it is unique. Almost everything occurs somewhere else in the corpus, in the particular main corpus. Incredibly repetitive, right? And as you'll see, we'll talk about this. The question is English just like this? We're going to get into that question in a minute, right? So as I said, the first part of this talk is all science. So, that's amazing. I mean, it's so incredibly repetitive, right? And as we allow changes, it doesn't change that much, right? So, so check that out, right? So, this is one edit, and then this is with edits and alpha renaming. So, if you allow alpha renaming, then, think about this, right? About 23 tokens, maybe 3 to 4 lines. It's all the same. About half of it is all the same, not all. Half of it is repeated, right? Okay. So this is kind of gives you an idea of why is it that automatic program patching seems to be so successful, right? It's because in most of the cases, if you have a bug, there's something else, or half the time, someone else in the code that's a fix for this bug, because somebody's written the same code somewhere else. So if you find the right piece and you rename it, it's going to be a fix, right? So this is what they were trying to prove in this paper, is that this is kind of a reason for why automatic program patching, a scientific reason why it's successful. I think they succeeded in doing that in this paper. Okay, so now turning on to exact matches, it's kind of in some ways even more remarkable. Right. So if you look at the exact match, so something like 60% of all the lines of code in the program are somewhere else. It's the same line occurs somewhere else, right? And not just single token lines, 6, 7 token lines. Actual line and actual 7 token lines, or half of it is more than half of it is somewhere else. And it's sort of even at 15, 20 token levels, it's still about 100%. Exact same sequence, right? Okay, so So that's C. What do you expect for C++? What's the shape of this curve going to be like for C++?
Hopefully less duplication.
Sorry, less duplication. Yes, right. Yes, hopefully we see less duplication. Okay. Right. So let's. I don't know if you can compare the two. So if you look at C, the 3-edit line stays at close to 100 to about 27, 28 tokens, right? And then we move to C++. It falls off faster, right? So there's a little bit of a more rapid decline for C++. Sorry, this is Java. I meant to show the C. Okay, there's C++. I don't know what happened. I'm sorry. I apologize. Something happened here. Okay, so the point about Java is actually turns out Java is more repetitive than C++ and C. And part of this is, because in Java you have a lot of like this syntactic redundancy, you have a lot of, import statements and so on that make it more repetitive. And then they've got a few more plots in the paper from specific projects. Different projects show slightly different characteristics. Right. So this was their. I think, in some sense, this paper really inspired us a lot. The question that immediately comes about is how does code compare to the natural language? Right? And this really matters because there's 30 years of work in statistical natural language processing that has been developed for the purpose of doing really amazing things. So if you want to use that, you want to understand the relationship between code and natural language, right? So the question is, how much repetition is there in code? When you compare code with natural language, how much repetition is really there? Okay, so I'm going to show you a series of zip plots. So I first want to quickly explain what a zip plot is. Okay, so a zip plot is kind of a way, it's just like a distribution. It's just a way to model a distribution. It's very commonly used in population properties, right, to show population properties. So the way it's usually plotted is, so it's a log-log plot, both the log scale. So it's very compressed, both on the y-axis and the x-axis. And on the x-axis you have log rank. Log rank meaning whatever it is you're measuring on the y-axis, you put the highest over here and the lowest over here, right? So the y-axis is typically something like income or population, right? So let's try population for instance to start with. So this is maybe population of cities, right? That's a typical thing that's done, right? So you take all the cities in China, for example, and you put the population on the y-axis, and the rank on the x-axis. So this is the most populated city in China, so Shanghai, and then you have Beijing, whatever, right? Nanjing, it goes down like that, right? So the rank of the city in terms of population, the y-axis is the population itself. Right, okay, so another thing that's typically done is income, right? So income, so who's take a country like India, who's the richest person? So Anil Ambani, so he goes here, and then it goes down from there and see what the population is. So the remarkable thing about many of these plots is that they're actually straight lines. Okay, so what does this mean? This is log scale. So for example, if we're thinking about cities, so this is 1,000, 10,000, 100, so if you think about, of course, the slopes are going to be different for population and for population of cities and income or wealth. There's no city with a population of 1 billion yet. Might be eventually, but not now, right? So you get these very peaky, there's a few incredibly common, incredibly wealthy people and a few incredibly populated cities, and then it drops like this, right? So it's it's kind of an exponential distribution, and this is a common way to show it. So why is it like this? Why does income and population show these things? Why do some cities get so populated? It turns out, if you look at social circles, the number of people you know, it also seems to follow this property. It turns out, if you look at the number of links that go into a web page, also shows this property. If you look at the number of methods that call a method, there is the in-degree of a method in a call graph. If you take methods calling methods call graph and you plot the in-degree of methods, it also looks the same. Right? So, why is it that cities should show something like this, where a few cities become phenomenally populated, the others are not? Same thing with income. Why is it that people accumulate enormous amounts of wealth and others don't? Why is it that a few web pages attract most of the links? If you think about it, most of the links, if you think of links as a limited resource, most of the links, big proportion of links are accounted for by a small number of web pages. So why is that? What is the physical phenomenon that leads? This didn't happen instantaneously, right? This happened over time. So something sort of tends to cause the wealth to flow upwards to the wealthiest people, or the populations to flow towards the most populated cities, or the links to go towards the most linked web pages. Thoughts? Ideas? If you were going to choose a city to move to, maybe you're not very, maybe you're unusual, I don't know, but if you're going to choose a city to move to, how would you choose a city?
The most populated.
Why?
Power law.
Say it again?
No, it's power law.
Power law, yes, yes. So the phenomenon is called preferential attachment. Okay. And what it means essentially is that when you have a lot of something, it's easier for you to attract more of it. Right? So if you already have a lot of money, it's actually easy for you to make more. Because you can start companies, you can take risks. And risk always comes with additional reward if you choose the right risks. You can influence government to develop policies that are more favorable to you to make more wealth. So all those things are possible only if you have money. And if you have money, you can accumulate more money. Likewise, if the city is well populated, then it has the features that people want. It has good infrastructure, it has good transportation, it has more cultural activities, more music, maybe more art. So people want to move there. If a web page already has a lot of links, then it's easier for people to find it. And if they find the web pages, then they link to it more. Same thing with citations, right? So if a paper already has a lot of citations, then you're more likely to cite it because you'll know about it, or one of your friends will tell you about it, so you'll cite it more. So this phenomenon called preferential attachment leads to these sorts of distributions. Okay. Now, the reason why I'm talking about it is we see this in natural language. Okay. So this is a zip plot of words in English and words in Java, words meaning tokens in Java. Okay. So what I'm showing here essentially on the y-axis is the percentage of the total corpus that is occupied by a particular word. So the x-axis is all the words that you see in English or Java. So in this case, we're considering about 100,000 different unique tokens. So words like the and and table and room and furniture. These are words. So each word occurs in the corpus at a particular frequency. So the is the most common word in English, for example. Right? So it occurs at a particular frequency. And so this is the least frequent word. This is the most frequent word. And the y-axis is the rank. So it's percentage frequency. Think of it as a probability. It's just a probability. So if all the words occurred at the same frequency, so every word in English is equiprobable, right? Then these lines would be flat, right? It's not that way. It's very steep, right? So the y-axis is the probability. So with the most frequent word in English occurs, is around 2% of the corpus, so it's percentage, right? And so it goes down from there. So you can see that it's fairly similar, right? English and Brown are fairly similar. Brown, by the way, I should mention, Brown is a very commonly used corpus in English. So it's a collection of various newspaper articles and some fiction and different things put together to make a common representative corpus of English. So they're very similar, right? You'll see that the most frequent Java tokens, most top few Java tokens, are above the brown line. It's a little, I'm sorry about we should have picked a different color because there's a little bit of color, cognitive dissonance going on there. But you'll see that the Java line, which is blue, is a little above. Do you see that? Which means that the most frequent tokens in Java are a little more frequent than English. That means Java is actually a little more repetitive at the high end than English. Okay. Now, also notice that the x-axis, the area under the curve, has to add up to, any guesses? It's percentage, right? So what should the area add up to? It's a probability, right? It has to add up to 1, exactly. Right? So if it's above, if Java is above Brown at the high ranks, then afterwards it has to cross over. If it's above somewhere, it must be below because the area has to add up to 1. Right? So you can see that Java at the high end comes below, at the very low end it's repetitive. So if you have a highly repetitive language, where it's really all one word being repeated over and over again, the line is going to be really vertical. That is, all the probability mass is going to be around the top 1 or 2 ranked words. Right? It's going to, and then the other words will hardly occur. Okay, so any questions about this? All right, okay, so now, instead of looking at one word, we're going to look at sequences of 3 words. Okay? So those guys looked at sequences all the way up to, 120 tokens. We're just going to look at sequences of 3 words. Okay. So this is really quite remarkable, right? So in Java, we see the repetitiveness really shoots up compared to English, right? So the most frequent trigrams, that is a sequence of three words in Java, really are way more repetitive than what we see in English. So what does this mean? And why is this? Why does language show so much more repetition? Why is language so repetitive and show the same kinds of behavior as population or wealth? Why is it that a few trigrams occur more often? What is the phenomenon that's driving it?
The vocabulary is smaller with respect to English, right?
In Java?
Yeah.
No.
No? The number of different... Oh, right, because you also have identifiers, right? Yeah. Ah, okay.
Yes. So we're going to talk more about identifiers in a minute. In fact, identifiers are made up, right? Identifiers are like German. It's like you don't have a word, you just make one up. Dopschiff, what is that? Dopschiff, Versicherungs, Gemeinschaft. I think it's one word for steamship insurance institute. One word. So, programming languages are like that. You just make up kind of things. So the vocabulary is very high. So what is it that's driving this in code and in English? And so there's 2 questions. One is, why is in English do we see the ZIF plot? Some words are occurring over and over again. And the second thing is, why is it that code is more repetitive than English?
Are there patterns inside, like substitute patterns? Or?
Programmers are less creative than
Yes, I mean, so people like to use patterns, certain kinds of things over and over again. So why is that, right? And so just backing up to English for a minute, right? So going back to the previous slide. Yes, this zip plot. The reasons for seeing the zip plot in income, in population, in social networks, has to do with preferential attachment. Right? What is the reason why this is observed in English? So then we can talk a little bit about code. Why is that? Why is it that we tend to use few words more often and most words very rarely? I mean, once you get past the 1,000-word vocabulary, it just is like nothing. I mean, you rarely ever see them, And by the way, this is not because, I'm not a big fan of English. English is crazy. I mean, I get confused all the time. I mean, I've been speaking English since I was 4 or 5 years old. In India, people ship their kids off to English school. Middle-class people ship their kids off to English when they're 4 or 5, and you're struggling to learn this language, and it seems very strange and bizarre. I remember my grandfather telling me English is a strange language. If you'll forgive it, he said it's because the English were strange. He worked in the British colonial empire, and he had all sorts of interesting ideas. He said the reason why the sun never sets on the British Empire is because they never see the sun. It's always cloudy. So very strange things like finite and infinite. What? Why isn't it infinite and finite? It's crazy. Anyway, so it's not because English is crazy. You see this. You see this in all languages. It's not really anything unique in English. All languages are like this one. So why is it that we use such a small vocabulary and the rest of it's so rare?
You start with a basic vocabulary and then you learn, right? And then the basic stays there and then you learn some.
You learn some other words, but most people never use the fancy vocabulary. So the common joke about English is that the words in this range are only used by first and second year college students because they want to show off all their. So why is this, right? So it turns out this has actually been extensively studied by people like Ziff himself. And this guy, Mandelbrot. So I had great fun once. I went to a German baker and I asked them if they had a fractal version of the Mandelbrot. He was not amused. Okay, so they've actually studied this, and their theory is essentially it has to do with efficiency of communication. Actually, it's a derivation, this mathematical derivation, that shows that if you're trying to communicate the most efficiently, that is the least effort for the speaker and the least effort for the listener. Remember, communication requires effort, right? Because I have to articulate the words, right? And the listener has to understand me because they're trying to essentially disambiguate what I'm saying in the presence of noise, distraction, and danger, right? So you want to have this very efficient communication. So it turns out if you model that, and you actually end up with this zip-file distribution. It's really beautiful. Why is code like that? Stay tuned. I think we'll have a paper coming out in a few weeks about this. So we're still working on it. We don't want to talk about it because we haven't worked out all the science yet. There's some maths that's still not clear, but we're working on it. All right. Okay. So code, I guess you could safely say whatever imperatives apply to English apply to code equally or more, because code has to be read, and the process of reading code is even more difficult than reading English. It's hard to understand code. It requires a lot of effort. Right? So whatever applies to code applies to English, and that's why you see the steepening of the curve when you get to Java. Questions about this? Other thoughts? Yes?
Maybe the programmers want to make the code more readable to who's maintaining it.
That's right. So because of the effort required in reading and maintenance, right? I mean, there's so many papers that say most of programmers' effort is spent in maintenance, right? So because you want to make it easier to read, you want to write something that they've already seen before. Because if you use something they've already seen before, then they're more likely to read it quickly and understand it. So you tend to write this very repetitive kind of code.
Or everyone is just copying from Stack Overflow.
Well, true, but I think a lot of the code that we have is probably predates Stack Overflow.
And also to talk about Java, there's this public static void, and we always have those groups of hooks that just belong together. They may shall be one single hook.
That's true enough, yeah. So that's what I would call annoyingness, right? So it'd be nice to have if you can figure out how to mathematically model that, then you can help programming language designers to do a better job of not being so annoying. Okay, so this is trigrams. What about fourgrams? That is sequences of 4 tokens. It actually gets worse, right? The difference between Java and English gets even more dramatic, right? So you see this even greater steepening of the thing, and you see again, it has to cross somewhere, right? Because the areas have blue lines where it crosses. And the reason why you see these flat lines is because sparsity. That is, you don't really see that many different ones because there's so many different possible foregrams, right? When you get to that range, and they just don't occur that often. The data isn't there enough. Right? So this is data sparsity problem. We'll get into data sparsity in the second half. I'm going to talk a little bit about estimating some of these statistical models if we have time. All right. Okay. So the question about public static, is an interesting question. So is this sort of repetition that we observe simply because there's irritatingness, right? This sort of stupidity that you see in programming languages where the same sequence of keywords are repeated over and over again. Is it that? Is that the reason why most of those highly repetitive things, just public static void and throw open paren new whatever, or this sort of nonsense, right? System.out.print. What is that? Where is that coming from? Good question. We'll look into that. So the question is, well, we have a lot of data, right? So we can just simply go through and get rid of all those things, right? So we can go through Java and get rid of all the keywords, right? And all the punctuations, all the open parens and open curlies and semicolons and pluses and throw all that crap out of it. Like, get it out of there, right? And then look at the rest of it. We can do that, right? Good. Question is, how do we do that for English?
Well, in text retrieval, there's a thing like subword removal, for example.
Very good.
They and all this.
Exactly. So in English they call them closed category words, right? So in Italian it would be ill and low and those sorts of things, and der and die and sich and all this in German. So in English, all the articles, the definite articles, the pronouns, the conjunctions, out the door, right? Get them all out of there, right? And then look at the rest of it, right? So what do you think will happen? More plots. Okay. So this really surprised us. So this is all unpublished. This is all new stuff. We haven't written up yet. So it actually gets worse, right? So what's left in Java? What's left in Prem? What's left in Java? Just identifiers, right? What's left in English? Nouns, adverbs, adjectives, verbs, right? Open category words is the only thing that's left over. So if you just consider those, Java remains much more repetitive. Okay, and this persists all the way to something like rank 10,000, even up to something like 60, 70,000 rank. Java is more repetitive than English. Question?
What's the role of APIs and shared libraries in this analysis?
That's a great question. We haven't done that analysis yet. It's actually going on right now. It's a good question. So your point might be that some of this is because of shared libraries. Right, I think that's a very good question. We don't know the answer to that yet. We're looking at it. Okay. So essentially, there's a lot of repetition in Java, and if we go to foregrams, the difference is even more dramatic. Right. Just like the trigrams to foregrams with all the keywords, it gets more dramatic. Comments, questions? Yes?
Does that mean that people are going to use the same identifiers?
Yes, they do. In fact, there's a number of interesting papers, I think done by some of the people in this room perhaps, on identifiers and the use of identifiers and how there are good uses and bad uses. Now, why would there be good uses and bad uses of identifiers? Well, it's because there are conventions about how you should use identifiers, right? And if you don't follow those conventions, people get very confused, right? So there's some really interesting work from Charles Sutton in Edinburgh called extremes. He calls it extreme summarization. So he actually develops a deep learning model of the content of code and tries to predict the identifier from it. And it's remarkably effective. And why is that? Well, it's because given a particular kind of method with a particular kind of semantics, you should choose a method a certain way. You know, if you don't, well, you know, you're being the bad guy, right? So, so they have this this kind of way of doing things, which is very interesting. All right, okay. So, you know, this is combining all kinds of English and Java in all sorts of interesting ways. So now, what about other types of English? So we looked at several different types of English.